We are going to start out our force unit by looking at Newton's laws of motion, which are sometimes considered kind of a basic, easy concept in physics. But let's not forget that Newton's laws, good old Newton, revolutionized science and quite possibly the world, and it took thousands of years for humanity to come up with these things. The Greeks, as smart as they were, didn't understand or couldn't describe motion in any sophisticated way. So let's, without further ado, move on to the laws. First law of motion, some textbook definition will call this the law of inertia, objects moving until acted upon, blah, blah, blah. I like to think about this as the law of balanced forces. And by balanced forces, I mean that the up forces are equal to the down forces, and the left forces are equal to the right forces. The sum of all of those forces are equal to the sum of the right forces. Another way of saying this is that the net force is equal to 0. When we have balanced forces, we have constant velocity motion, or just constant velocity. Now that can be either remaining motionless. Most people don't have a problem with that. Not motions, motion, L-E-S-S. If you quizzed elementary kids and told them a little bit about forces, and you had a motionless object, they would be able to pick out that the forces cancel out or there are no forces. But the one that tends to trick the novice physicist, I guess they're not physicists yet, is that you can have moving at a constant speed, and direction, for being precise, direction. So the idea that Newton changed about why things move, the Greeks thought they moved because you gave them impetus and that they would stop moving because that impetus somehow kind of petered out. But this idea right here was novel. He said, no, things stop moving because other forces stop them. If there were no other forces stopping them, they would just keep moving forever. People weren't used to seeing that happen because that requires a frictionless or very low friction environment, so that's not what we experience in the everyday world. But if you were out in space and hucked a baseball far away from any other planets or gravitational forces, it would just keep going forever. Even on ice, if you have an ice hockey puck and you smack that hockey puck, it will keep going at a constant speed for quite a while, or nearly constant speed. Alright, so there's first law. Second law, somewhat similar. It relates unbalanced forces. So the sum of the forces, aka the net force, is not equal to 0. And in fact, well, I'll come back to that. If that happens, I forgot an A in here, didn't I? Unbalanced. Alright, throw an A in there. If the net force is not equal to 0, then the result is not constant velocity, but changing velocity. And we call changing velocity acceleration. Alright, and Newton went further and he said we can make a law, second law of motion, that is usually written like this, but if you rearrange it, since we're talking about accelerating here, the acceleration is directly proportional to the force and inversely proportional to the mass of the object that is accelerating. So if you understand algebra, that should make sense to you. Okay, third law is a bit different. It doesn't deal with balanced or unbalanced forces. It deals with action-reaction pairs. Action-reaction pairs. So this, in the first and second laws, you're just looking at the forces acting on an object. This one deals with the forces of that object acting back. So this is sometimes said for every action there's an equal and opposite reaction. By opposite we mean the opposite direction. So let's take a couple quick examples. If you, stick person that you are, push on a box, say you push on it with 10 newtons of force, then the box pushes back on you. Now we don't draw this on the same free body diagram. We draw you, so this is dot is you, that dot is the box. The box pushes back on you with 10 newtons of force. So the key here is that the action-reaction pairs, the equal and opposite forces, are not on the same free body diagram. Whereas with the first and second law, we're talking about all the things acting on an object, not really considering what that object is doing back to those things. Let's jump to a couple of problems that we're going to look at. First one, good old stick person again, is pulling on a box with a rope at an angle. There's friction. How fast will it be moving after 10 meters? So often the problems you will see are going to combine some analysis of the forces and some analysis of the kinematic motion. And the link between those two things is acceleration, because we have acceleration in F equals ma, and then we obviously have acceleration in our kinematic equations. So sometimes we'll use kinematics to solve for acceleration, then plug that in to solve for force or mass or whatever. And sometimes we'll go the other way. We'll use the forces to find the acceleration, then plug that into kinematics. So let's set up this one and see which way we have to go. So I've got my box here, 100 kilograms. I've got my friction force of 30 newtons. I've got gravity and normal force acting on this. Don't know the magnitude of those. I could probably solve for them if I wanted to, but I might not have to. Got a 100 Newton force of tension here, 35-degree angle. Here is tall, skinny stick person. This rope goes over their shoulder or something. They're hanging on to it. Alright, there we go. Here is our setup. And we want to know how fast it's moving after 10 meters. So I'll put my kinematic stuff over here. I've got delta x is 10. It was initially at rest, so v naught is 0. And I want to find my final velocity. Acceleration I don't know, and time I don't know. Okay, acceleration I can find though using the force stuff. Time I'm not going to worry about, and that gives me a clue as to which equation I'm going to use. I'm going to end up using v squared equals v naught squared plus 2a delta x. So I just find a, and then I'm good to go. So I come over here and I want to look at the forces. Now we're assuming this box is not coming off the ground. If you analyze the forces, it wouldn't. You're not pulling hard enough. Anyway, we don't really care about the vertical forces because all we care about is the horizontal motion. So we just need to look at the sum of the forces in the x direction, and those are going to equal mass times acceleration. The forces I have the tension here is 100 newtons, but it's not in the x direction, it's at an angle. So I'd need just the x component of that tension. Then I have the friction force pulling back the other way. Mass is 100. Acceleration is what I'm going to end up solving for. To find the x component of that tension, I take the total tension. Now the x is going to be the adjacent side, so I want cosine of 35 minus 30 equals 100 times my acceleration. 100 cosine of 35 comes out to be 81.915 and change, minus 30 equals 100. Acceleration, you can do the rest of the algebra. You end up with an acceleration of 0.51915 meters per second squared. Plug that guy in over here. 0.51915. Then we can jump down to this guy. V squared equals 0 plus 2 times 0.51915 times 10. That comes out to be 10.383, but be careful, that is v squared, not v. So we take the square root of both of these guys, and we will get a speed of 3.22 meters per second after our poor stick man has dragged this box over here 10 meters. So the box is now, the front of the box is there. Okay, one more example. here we have a, is it? Just a small mass, okay. Hanging from a string in your car. You can use this as an accelerometer where you can measure angle theta and you could calculate your acceleration. Probably shouldn't do that while driving. Alright, so if we have an acceleration of 1.2 meters per second squared, we want to know what the angle is going to be, and then when it's moving at a constant velocity of 90 kilometers per hour, what will the angle be? So let's get to it. We already have our free body diagram here nicely done for us. The only forces acting on that ball, even though it feels like it's being pulled back, that's not really what's happening. That's just inertia. The car is going forward, and then the car, through the tension, is pulling the ball forward with it. So the acceleration is in this direction. We've got forces there, there, there. Let's see if we can make sense of this. If you don't know where to start, you should always write two equations, one for the sum of the forces in the horizontal direction, equals ma, and one for the sum of the forces in the vertical direction. Okay, so horizontally, this guy is all vertical, so none of that's horizontal. Here, a component of my tension force is going this way. So for now, I'll just call that Ftx. That's equal to ma. I know I've got acceleration horizontally. That's the 1.2 I was given. Over here, the sum of the forces in the y direction, I have a component of tension going up. So we'll call that guy Fty. I also have gravity going down, so minus mg. Now in this direction, the ball is not accelerating. All of my acceleration is horizontal, so I can set this equal to 0. What I really want to, well, no, I guess we'll keep going. Alright, so to find Ftx, that's the total tension, times, let's see, is it sine or cosine? It's going to be cosine of theta. Theta is what I'm going to try to find, right? Equals ma. Now, I've got acceleration, but I don't have tension or mass, so I can't solve for theta yet. Let's see if anything over here will give me a hint. Fty is going to be Ft sine theta. Then we'll go ahead and move the weight to the other side. So we've got this. And seems like we have a lot of unknowns still. So if I solve this for tension, plug it in over here, then I will get tension equals mg over sine theta. Plug that in. I've got mg sine theta times cosine theta equals ma. Now things are looking good. My m's go away. I've got a couple of thetas, but I can combine those. And then I divide the g across, so I end up with tangent of theta equals the acceleration divided by the gravitational acceleration. And all we need to do now is take an inverse tangent. We're given acceleration 1.20 over 9.8. This works out to be just shy of 7 degrees. Alright, so that's part A. Part B, constant velocity, you probably already realized. In that case, acceleration is 0. If you're not accelerating, you probably already know it's not going to be at an angle, but you can still plug in 0 for acceleration here, and that will give you a big fat